is a nice way of showing how to get that in the case of Laplace's equation. Okay. So so at the end of the day, we'll have, well, maybe not the end of the day, but probably on Wednesday. Okay. We'll have something like a fundamental solution on a bounded domain. Okay, and in particular, we're going to look at Laplace's equation on a disk. Okay, so the Laplacian of u equals 0, u is equal to f, and x is going to live in the ball centered at 0 with radius a. So then its boundary is centered at 0 with radius a. Okay, and this lives in R2, so we're looking on the plane. Okay, so this is nice. We'll get a nice sort of 2D separation of variables problem, but we're going to go to polar coordinates. So how do we do this? Well, we take r cosine phi and make that x, and r sine phi and we make that y. And we'll separate the Laplacian. Okay. And so in the process, what we get, we can work out that that operator becomes the second derivative in r of u, 1 over r, u sub r, plus 1 over r squared, u phi phi. You could do this by chain rule. And this is defined in our polar coordinates. Okay. All right. Let me be careful about my boundaries here. So yeah. So we only want to hit that angular value at 0 or 2 pi once. Okay. And we sort of run into singularity issues at 0, so we'll leave 0 out. And then a is the boundary here. Okay. So this is gotten by you know, that change of variables, right? And our boundary condition is now easily defined by setting r equal to a, and we can verify. Okay. Okay. We need one more thing though, right? Because we're kind of leaving the phi coordinates open. And so the last thing we need is periodicity, right? Because as we go around the angular coordinates, right? So this is r here, right? This is a, and this is our angular coordinate here, phi, right? It's going to come back around to here, and we need our solution on the interior to be continuous. So it's enough to just require once continuous differentiability and the with periodic boundary conditions. Okay, and so our periodic BCs are going to be u along r0 is equal to u along r2 pi, u sub phi r0 is equal to u sub phi r2 pi. Okay. And this gives continuity, and it ensures uniqueness. Okay. I also, as I said, we have a singularity at r equals 0. And that essentially requires boundedness at r equals 0. Okay. All right. So we need to make sure that nothing funny happens at 0. So the main thing we just need is that as we take r down to 0, that our solution doesn't blow up. Okay. All right. So this is how we piece things together in polar coordinates. Now we can essentially just take off and use our separated solution assumption. Okay. So I'm going to call these r and h, these functions. And when I plug into PDE, what do I get? I get, if I multiply through by r squared, I get r squared capital R prime prime of r plus 1 over r prime of r divided by r of r. So I did the usual thing I do. I plug in and then I divide by r and h. Big R and h prime prime of phi divided by h of phi is equal to 0. Okay. So then what are we going to do? We're going to move the h terms over to the other side. We'll say there's r terms on the left-hand side. There's phi terms on the right-hand side. Both have to be constant. We'll call that constant lambda. And then we'll have a, we'll have a pair of differential equations, and one will give us a nice boundary value problem. Okay. All right. So I'll write that down on the next slide. If I can move on. Okay. So we get that h prime prime of phi, h of phi is equal to minus r squared r prime prime plus 1 over r prime over r. We'll say this is equal to, make sure I'm getting this right. Yeah, minus lambda. Okay. So then if I take h prime prime of phi equals minus lambda h of phi, okay, then I can solve this for the solution in terms of phi. Okay. Note that our boundary conditions become h of 0 equals 2 pi, h prime of 0 equals h prime of 2 pi. Okay. And this is going to give me that h needs to be a periodic function, okay, on 0 to 2 pi. We know what those periodic functions should be. They should be trig functions, right? So I either have a 0 over 2, just a constant, or lambda 0 equals 0, or I have the sum of sines and cosines. And lambda n in this case is n squared, okay? And so these are all greater than or equal to 1, right? And in particular, n is going to be the positive integers in this case, okay? if I took the negative integers, then I would essentially just get the flip of those. So I don't need to worry about the negative integers. Okay. So those are our basis functions in H, right? What do we get in terms of R to pair up with those and give us our solutions that we're going to add up in order to get our total solution? Well, we now know that our eigenvalues are going to be lambda n is equal to n squared. One of these is kind of special. It's the n equals 0 case. And so that's going to be a little bit different than the n greater than 0 case. But we can write out our problem now for R in terms of these eigenvalues, right, that we've gotten already. So let's deal with the n equals 0 case first. Let's get that out of the way. Okay. Well, in that case, we have r squared, r prime prime, plus r prime is equal to 0. Okay. One solution to this problem is just a constant, right? Another solution to this problem that you can get by integrating up and then you can use separation of variables is natural log, okay? So the general solution in this case is just the sum of a constant and a natural log, okay? So we get r of r is equal to, I'll call this C0 plus D0 natural log of r. I'll call it log of r, but that's our natural log of r. Okay. So this should look familiar, right, in terms of Laplacian, because actually it's our it's a general form of our 2D fundamental solution. Okay. But before we move on, I'm going to apply our additional boundary condition. Remember that we have at r goes to 0, okay? It's not your typical boundary condition, but it's a boundedness condition, okay? So what that means is that as I take the limit as r goes to 0, I want to make sure that nothing's blowing up, okay? Well, the log is going to blow up as I take r to 0. So this actually means that I need to set d equal to 0, okay, so that the limit as r goes to 0 from above of r is finite, okay? Log would blow up, okay? So we want to get rid of the log there. So because we have free constants in our H solution, we don't need to keep the free constant on our R solutions. That would be redundant. So we're just left with, let's say, R0 equals 1. Okay. What about the other solutions? Okay. N greater than or equal to 1. Okay. Well, in this case, we have a special kind of ODE, and they have power function type solutions, right? So whenever you have this sort of r squared, r, and then a constant successively in second order or more differential equations, the solutions are power functions. I think they're called Euler somebody else's name type equations. Talk about them in ODEs. Okay. So so these have power functions as solutions. If I plug this in, right, if I plug this ansatz in up here, right, I'm going to get an alpha coming down for the r prime term and an alpha minus 1 coming down for the r prime prime term. So I get alpha alpha minus 1 plus alpha is equal to n squared. I can simplify this considerably because this alpha cancels here with this alpha. I just get alpha squared equals n squared. So that means that alpha is equal to plus or minus n. Okay. But remember, again, I need a bounded solution. So the alpha equals minus n is going to be bad, because then as I take r goes to 0, that's going to blow up. Okay. So for a bounded solution, okay, I need to take Rn of r just equal to r to the n. Okay. And in fact, this even works for n equals 0, because that would just give me back 1. Okay. So this is my general solution for n greater than or equal to 0, r to the minus n. Again, this blows up, so we're getting rid of it. Okay. So I have my constituent solutions. I'm pretty close to being able to construct a full solution. I don't think I'm going to finish today though. Okay. And so so what we have is that our harmonic solutions, okay, are going to be un r phi. We've built them now. We have r to the n, a n cosine n phi plus b n sine n phi n greater than or equal to 1. And then down here, I just have a 0 over 2 for n equals 0. Okay. So our series solution then is going to be in total a 0 over 2 plus the sum from n equals 1 up to infinity, r to the n, a n cosine n phi plus b n sine n phi. And with this, I can now satisfy my boundary condition. Okay. So my boundary condition now is going to be u of a phi equals f of phi. Okay. This is equal to a 0 over 2 sum from n equals 1 up to infinity. Should be a plus sign there. A to the n, a n cosine n phi plus bn sine n phi. Okay. So what do we do? How do we get the coefficients? We need to exploit orthogonality of our eigenfunctions, right? We have an infinite series. The only thing that's happened now is that we had this a to the n term out in front, but that's okay. That's just going to show up in our coefficient equations. Okay. So if we use orthogonality, okay, of sine and cosine, what we get then is that an and bn, I'll write this sort of in vector form, is equal to 1 over a to the n pi integral from 0 to 2 pi our boundary condition f of phi, and then the ans we get by integrating against cosine, the bn's we get by integrating against sine, the phi here. This even works because of the scaling that we've done for n equals 0. So it works for n greater than or equal to 0. Okay. And so that's our full solution. Our coefficients here are given by these integrals, right? As we usually have in separated variable solutions, and we have this infinite series solutions. Next time, what I'll do is go a step further and say, well, based on the form